Good evening. Today we would be discussing about the summary of week 3 lectures, and also we will discuss about the assignment questions from the previous 3 weeks, starting from the week 0, 1 and 2. Later, as far as this week is concerned, if you have any further questions, that we will discuss. So in the week 0, actually, before you could have started your lectures itself, there were few questions that needs to be answered. If you could have remembered, where the first question was, which of the following consistency property of soil is critical for pavement upgrade? So by that time, you might not have the knowledge about this plasticity index and all these details. Yet, which consistency property of the soil is critical is what they were asking. So, out of four options, consistency properties are this shrinkage limit, usually liquid limit, plastic limit. These are the consistency properties. The California bearing ratio test, California bearing ratio and proctor density are not the consistency properties. So the option could be either plasticity index or the shrinkage limit. So out of these two, the main important consistency property is plasticity index, because we know that the plasticity of the soil is what which plays a critical role in designing the or selecting the soil for the pavement construction. So plasticity index is the one of the consistency property or main consistency property. If we come to the second question, which was resilient modulus is defined as the ratio. We know that we calculate the resilient modulus based upon the recoverable strain. So when the soil or aggregate material, when it is subjected to repeated number of load applications, after So after particular number of load applications, what just happens is the amount of recoverable strain and the amount of unrecoverable strain. There will be two parts of the strain, where you can see that the amount of non-recoverable strain remains constant and you will be only considering the recoverable strain. So derivative stress and recoverable strain are the ones which we would be using to calculate the resilient modulus. And in the third question, which of the following pavement layer is typically used for drainage? So we have different pavement layers, as we already know, starting with subgrade from bottom. Above that we'll have granular subbase, above that granular base, above that it will be bituminous mixture. Bituminous mixture can be laid in multiple layers. So if we just talk about the granular base and subbase, so this granular base is immediately placed over the subgrade, and above subbase there will be a base. So this subbase, actually why we place is, whenever there is a rainfall from the top, the water whatever enters from the top, when it reaches to the subbase, we do not want that water to again pass through the subgrade. So from the subbase sides, we wanted that water to be drained. So that is the main purpose of granular subbase, which is used for the drainage. And in the fourth question, which of the following properties of bituminous mixture cannot be measured in the laboratory? So as far as the mixture specific gravity tests are concerned, which we haven't clearly discussed, but still, when you take the asphalt mixture, you can actually calculate all the bulk specific gravities and apparent specific gravities. So effective specific gravity of these is difficult to calculate, which actually indirectly will be calculated from the other specific gravities. That is the reason why they are asking which of the properties cannot be measured in the laboratory. This can be calculated based upon the other details, but directly using the experiment we cannot be calculating the effective specific gravity. So when we actually discuss about the specific gravity tests and aggregates in the upcoming lectures, We will be discussing this in detail with the images so that you will get the clarification between what exactly is the apparent specific gravity, effective specific gravity, bulk specific gravity. So as far as this is week zeros, this week's assignment questions are to test your initial knowledge before you are taking any lectures. Which of the following statement is true? So if you take the first option, with increase in temperature, the stiffness of bitumen decreases. Yes. If the bitumen is very hard and if you keep increasing the temperature, it becomes soft. So when it becomes soft, its stiffness will be decreased. Correct. With increase in rate of loading, the stiffness of a bituminous mixture increases. So what they are talking is, when I say with increase in rate of loading, let us say there is a vehicle moving with 30 kmph on the pavement layer, and if there is another vehicle moving with 80 kmph. So the rate of loading, when I say 80 kmph is more. So whenever there is a increase in the rate of loading, so the vehicle will be moving very quickly. So the amount of contact time between the vehicle bottom and the pavement is very less. So the load contact and the duration of contact is very less. In those cases, the bitumen will not be deflected much because the contact time is very less. In that times, the bitumen behaves as a very stiff material or elastic material. For example, if there is a standing vehicle, if you take the parking space, vehicle will be standing at particular pace. So on the pavement, if you keep the vehicle for 1 hour, the amount of load transfer would be more, the amount of deflection would be more. So in those cases, you can say that the stiffness would be reduced. But here with increase in rate of loading, stiffness of the bituminous mixture increases. And the third option is bitumen is a hydrocarbon. So this also we already know. If we don't know, in the upcoming lectures, we will be discussing how this bitumen we call as hydrocarbon. So all these three options are actually correct. Fly ash reacts with which hydration product for the formation of cementitious gel? So fly ash is a byproduct from the manufacturing unit. So when this fly ash reacts with the water, so this hydration product will form a cementitious gel. So they are asking, when fly ash reacts with which compound, there will be a formation of the cementitious gel. So when I say cementitious gel, in the concrete, cement concrete especially, calcium silicate hydrates, there is a CSH gel which will be formed when this calcium hydroxide is reacts with the fly ash. So the byproduct will be cementitious gel. So if you see all these three options, these three options are actually the cementitious gels. So after reacting this calcium hydroxide with the fly ash, you will be having this remaining three. The question is, to form these remaining three, fly ash should be react with which? That it has to react with calcium hydroxide. The design grade of dry lean concrete is equal to. When you take the concrete pavements, so unlike in the flexible pavements, you have DLC, dry lean concrete, and above that you will have the PQC, pavement quality concrete. So the topmost layer or the topmost slab will be with higher grade concrete. Below DLC will be of lesser grade concrete. So they are asking what is the design grade of DLC if you want to construct the pavement concrete. So in general that is M10. So those were the week zeros assignment questions. So as far as the week 1 are concerned, which test parameters are more critical to evaluate the response of granular materials to be used in the pavement construction? So unlike the asphalt material, granular and soil are completely different. So here you can see there are four factors. One is the time, temperature, moisture content and confining pressure. So which are more critical? If we take the bitumen, we can directly say that temperature is more critical, because with increase in temperature, the stiffness would decrease. With decrease in temperature, stiffness would increase. In addition to that, bitumen is a viscoelastic material. You can see its changes in the chemical properties and also its behavior due to temperature. But as far as the granular materials and also soil is concerned, temperature is not of that concern. If you take the sand, whether it is at 60 degrees or 50 degrees, you can feel that it is hot. Other than that, the behavior of the sand will not be changing, even the aggregates. So temperature is not. So it could be time, moisture content and confining pressure. Let us take the time. So if I apply for 1 hour of vehicle load and if I apply 10 minutes of vehicle load, will there be any change in the response of the granular material? And the moisture content, especially the change in moisture content would cause a lot of response differences in the granular materials and also soil and the confining pressure. So this remaining three would be the main important test parameters. Temperature might not be that much important for granular and soil materials. In a flexible pavement, the loading period. So if you could have seen a vehicle has a wheel at the top and let us say a load of 20 kilonewtons is applied from the wheel. So just at the bottom of the wheel, there will be a lot of stresses. As you move from top to bottom, stresses will be reducing because at the top only one layer is taking that in contact with the wheel bottom. As you move down, that load will be distributed to the wide area. As the load will be distributed to the wide area, so with the increase in the question is the loading period increases with increase in depth or decreases with increase in depth or it remains constant with increase in depth. So as you are moving from top to bottom, the loading period increases with increase in depth. You can see the first option. If a particle of size d has reached a height of 164 centimeters from the surface in 0.5 seconds, when allowed to freely fall in the water, what will be the size of the particle? Viscosity of water is given, unit weight of solid is given, unit weight of water is given. So this is a hydrometer problem. So we have allowed a particle of size capital D freely to move from top to bottom. Then it has reached around 164 centimeters from the top and the time required to reach that would equal 0.5 seconds. So they are asking what must be the size of that capital D or size of the particle so that in 0.5 seconds it has reached 164 seconds. So we already know this formula, velocity equal to d square by 18 eta into gamma s minus gamma w, where d is nothing but the size of the particle. Currently we do not know. Eta is the viscosity of the water, gamma s is the unit weight of the solid, gamma w is the unit weight of water. We know all the information, we do not know the capital D, we have to determine the capital D. So how do we calculate the velocity? Velocity, because we have given the distance travel in 0.5 seconds, we can calculate the velocity. If we substitute, so if we substitute all remaining details, we can calculate the particle size. So it was 6 centimeters. And if you take the next question, the meniscus correction can be evaluated using. So in the hydrometer, we would be doing the meniscus corrections using distilled water. Because when you take just the distilled water, the meniscus would be of meniscus would have difference from when you have mixed with the suspension. So the difference between the meniscus value for distilled water to the suspension is what we use usually. So that is distilled water. The range of moisture content for which the soil will remain in the plastic state should be dashed for the pavement application. So plastic state is specifically they are asking because the main feature of consistency property for soils among all liquid limit, plastic limit and shrinkage limit is the plastic limit. And if you take the range from liquid limit to plastic limit, that range is what we call as the plastic state. So if that range is a very wide, that means that for wide range of moisture contents, the soil is still in the plastic state. We do not want our material to be in the plastic state to be stronger or to be withstanding the pavement load. So we want that to be very narrow. So here the question is the range of moisture content for which the soil will remain in the plastic state should be always narrow. Which of the following statement is true? So, four statements have been given. Residual soils are generally inorganic. So, how do we actually say the soil is residual? So, whenever we have a bigger rock, then those amount of soils from the rock which are insoluble or which cannot transport from one place to another, they stay at that particular place and we call them as residual soils. Usually they are inorganic, that's why they are insoluble and they won't be mostly transported. So the option 1 is correct. Alien soil is formed by the deposition of suspended metals from the rivers. And let us say 2 we don't know what the answer is. Let us come to the option 3. Sedimentary soils are formed by the deposition of metals by wind. No, sedimentary soils are formed. We cannot say it is because of wind. Sand dunes and calcite silts are of alien soil. So we know 1 and 4 is correct. Whether 2 and 3 is correct or not, we don't know. So where is the possibility of 1 and 4? It is option C. So we can select that. And if we come to the 7th question, the closure length of soil at which the number of blows is recorded in the liquid limit test is equal to. So while conducting the liquid limit test, we have a bowl apparatus where we will be adding the particular amount of moisture content to the soil, and we usually make a groove in the middle and we try to give the blows. So that groove with number of blows comes to closure. So we don't want entire groove to be closed, but at least a particular length, if that groove gets closed, we can consider that moisture content at that number of blows as the blows corresponding to the liquid limit. So they are asking in the question, what is that length of the groove that has to be closed? So 12.5 mm is the length of the groove. During field visit, if you have quickly identified the plasticity characteristics of subgraded soil, which test will you perform? So here if we see the options, Proctor density test, this you have to perform in the laboratory. Casagrande liquid limit test, this also we have to perform in the laboratory. Sieve analysis needs to be done in the laboratory. That means this will require some apparatus. But if you see the shaking test, if you could remember, you can hold the material in your palm and you try to dab it, then you can see the amount of moisture that is getting settled, separated or segregated can be seen. So shaking test is the one which we usually do in the field visits. And if you come to the 9th question, sieve analysis was done on a 5 kg soil sample encountered in the field. The cumulative weight retained on 4.75 mm and 0.075 mm was 1000 grams and 2000 grams respectively, and plasticity index of fine grained soil in the mix was found to be 45% and 10% respectively. The soil class as per USC classification system and Indian standard classification system are. So if you see the options, 3 of them are either organic or silt and one option is either clay. So first we have to confirm whether the soil is a which type. So if we see the classification chart, so this is the plasticity index limit 0.73 into liquid limit minus 20 is the equation. So using that equation, we can actually calculate what is the limit of plasticity index. So liquid limit is already given as 45%. If we substitute, we can get that plasticity index is 18.25, which is the limit. But in the current problem, they have given plasticity index as 10. So our plasticity index is lesser than the limit. So this is the limit. Our plasticity index is less than that. That means our soils fall on this region. So you can say our soil could be either organic or silty soil. Now we have to confirm whether that is highly compressible or low compressible. So if you consider US classification system, high compressibility or low compressibility is based upon liquid limit. If it is less than 50%, we call it as low compressible. If the liquid limit is more than 50%, we can call it as high compressible. Here the liquid limit is less than 50, so we can directly say that it is a organic but low compressible. But if we consider the IS classification system, the only difference is the distinction is not just based upon liquid limit at 50, but it is based upon 35 and 50. If the liquid limit is less than 35, we call it as low compressible soils. If it is in between 35 to 50, we call it as intermediate compressible soils. And if it is more than 50, we call it as highly compressible soils. So our liquid limit is 45%, which is in between 35 and 50. So that is intermediate. So according to the US classification system, the value is the classification is either OL or ML, and according to the IS classification system, it is OA or MI. And if you come to the 10th question, a hydrometer analysis was conducted with 50 grams of bovine-dried soil and a volume of soil suspension, 10 centimeter cube. The hydrometer reading after 60 minutes of commencement of test was recorded as 19.50. The meniscus correction was observed to be 0.52. Assume the specific gravity of soil as 2.65. Calculate the percentage final. In order to calculate the percentage final, we know this is the formula. So what are the unknowns here? Specific gravity is already given 2.65. Weight of the soil we know 50 grams. Corrected hydrometer reading is what we needed. Initial reading is 9.5. There was a meniscus correction mentioned by them, which was 0.52. So whenever we have meniscus correction, so whether it in order to correct the existing hydrometer reading, the meniscus correction, let us say if the value is 0.52, we have to confirm whether it is minus 0.52 we have to do or plus 0.52. That means the correction is negative or positive. So while taking the reading, the meniscus is because of the capillary action and because of which the reading is taken at higher level. That means at the top. So at the top the values are less. So you need to deduct that. So after that, if you substitute all the values which are given, then you can get the value as 64.3. And if we come to the week 2, if an woven-dried soil have a weight of 2400 grams, is compacted in a 1000 centimeter cube cylindrical mold at a moisture content of 6%, calculate the bulk unit weight of soil. This is the simplest problem. We already know dry unit weight of soil equal to bulk unit weight by 1 plus water content. Currently, dry unit weight has been given. Water content is 6%. We need to calculate the bulk unit weight. So the answer is 2.544. The second question is moisture content at which shear strength of soil is maximum. So they are not asking the moisture content at which dry density is maximum. We know that the moisture content of optimum moisture content is the moisture content at which dry density is maximum. So there are two parts. One is left side of OMC, another is right side of OMC. Left side of OMC is called as dry side of OMC, Right side is called as wet side. Now we have to ensure whether the dry side is a right side of OMC is the place where shear strength is maximum, or the right side, wet side. So shear strength would be usually maximum when all the clay or soil particles are flocculated, so that they will have better compaction. When they are dispersed, when they are arranged in a particular order, shear strength will not be maximum. So if we have already discussed that on dry side of optimum moisture content, the soil is in the flocculated structure. So in that side, the shear strength of soil would be maximum. So on the dry side of OMC, in dry density and water content curve. For subgrade soils used in the construction, the optimum moisture content is determined using. So when you want to determine the optimum moisture content, we would be using the CBR and repeated triaxial test to understand the strength of the soils. Both standard Proctor test and modified Proctor test can be used to determine the OMC, but in the pavement construction, we consider modified Proctor test for the determination of the OMC. Which type of compaction is suitable for sandy soils? So sandy soils are actually having lesser cohesion, as we already know. So we need to give the vibration so that they would be compacted well. So out of 4, vibratory compaction would be more suitable for sandy soils. The shear stress on principal plane is. So this is also a very easy question. Principal plane usually is the plane where there is no shear stress. So that would be 0. In a triaxial test, 50 kilonewton per meter square of confining pressure is applied. So on the sides we have applied 50 kilonewton per meter square. Calculate the major principal stress if the deviating stress at failure is 54 kilonewton per meter square. Deviating stress is the stress which is being applied normally from the top. So that is given. Confining pressure from the sides is given. We need to calculate the major principal stress. So we already have the relation between major principal stress to deviating stress and confining pressure. So this is a direct formula. For example, how will we determine the major principal stress? It is the combination of deviating stress plus confining pressure. Sigma 1. When I say major principal stress, that is nothing but the sigma 1. Deviating stress is sigma d. Confining pressure is sigma 3. So sigma 1 would be sigma d plus sigma 3. So directly it would be 50 plus 54, 104. During a triaxial test, diameter of the specimen is 100 millimeters, height of the specimen is 200 millimeters. The recoverable deformation at the confining pressure of 138 kilopascals and a deviating stress of 103 kilopascals was found to be 0.112 mm. Calculate the resilient modulus. Resilient modulus is usually any modulus. It is exactly like elastic modulus. When we calculate the elastic modulus, it is a ratio of stress to strain. Here the stress is the deviating stress, but the strain is the recoverable strain. So in the current problem, we have been already given the deviating stress of 103 kilopascals, but recoverable strain is not given. But we have been given recoverable deformation. So if we already know the recoverable deformation, we need to calculate the recoverable strain. To calculate the recoverable strain, strain would be this 0.112 divided by. So this is the deformation occurred, but initial height of the specimen is 200. So 0.112 by 200. Then we can calculate the recoverable strain. If we know the recoverable strain, deviating stress is already given as 103 kilopascal. So the answer should be 183.9. In the pavement design, the value of CBR is used for. So why do we usually calculate the CBR? The option 1 is selection of soil for the construction. 2 is estimating the value of plasticity index. I think we are not estimating any plasticity index from the CBR. Third is calculation of resilient modulus. There is a chance CBR is not important for pavement design. So the option calculation of resilient modulus. So in the design, pavement design usually using IRC 37. If we know the CBR of the soil, we can actually calculate the resilient modulus. The standard deflection at which the modulus of subgrade reaction is calculated. So we did the plate load test to calculate the subgrade reaction K. So when we apply a load and the corresponding deflection we noted down, then the load corresponding to the deflection of 1.25 mm is what we have considered to calculate this modulus of subgrade reaction. Which of the following is the key factors for swelling and shrinkage? So when we have discussed about the chemistry of how water is being reacting with the soil, so swelling and shrinkage is because the soil is actually reacting with the water and there is a phenomenon happening. So out of the 4 options, if you see temperature, humidity, compaction characters compared to these 3, the formation of diffuse double layer, which we have already discussed, is what the main key factor for swelling and shrinkage of the soil. So those are the questions from week 0 and then week 1 and 2. Those were the assignment questions. And as far as the week 3 is concerned, mostly in the initial lectures, the formation of aggregates or rocks, how they have been formed, and followed by the crushers. How did we use the crushers to get the aggregates of designated sizes required for the pavement construction were discussed. For example, during the plate tectonics, let us say when the lava from the bottom of the earth, when it is moving from bottom to the outsides, on its way in the transportation, it can either get solidified below the earth crust itself, it can come to the top of the earth and it can get solidified. So igneous rocks are formed due to the solidification of this lava. Once igneous rocks are formed, those igneous rocks have been the source for the formation of sedimentary, and later metamorphic rocks are usually formed from both either igneous or sedimentary rocks. And those bigger rocks, after blasting, then they will be subjected to the crushers to reduce their sizes so that it would be useful in the pavement construction. And in addition to that, we have seen about the aggregate packing characteristics. So when we have aggregate gradation, that means when we have different sizes of aggregates, for each size of aggregates, how many percentage of aggregates I need to consider so that in my total aggregate count, I can have a densest packing possible. What is the purpose of densest packing? When the load is applied at the top of the pavement layer, we need to ensure that there should be most contact points between each aggregate so that large amount of load can be transferred from top to the bottom subgrade layer. For that, we need to have a densest possible packing. But when I say densest possible packing, it doesn't mean that there should not be any air voids. It should not be like zero air voids. If there is zero air void, what would happen? So in summer, whenever bitumen temperature is high, if the bitumen wants to expand, there will not be sufficient amount of space to expand. Thereby, the softened bitumen, whatever it is there during the summer, it will be coming to the top of the pavement layer. That phenomenon usually we call it as bleeding. Most of the times on pavement top layers, at particular places, we can see some amount of bitumen used to come to the top and it looks like a black color patch. That is a bleeding. That is because insufficient amount of voids are there inside the asphalt mixture, which is causing the bitumen to ooze out outside the mixture. So we need to have minimum air voids, and at the same time the aggregate should have most densest possible packing, so the load transfer would be easier and efficient. So one of the theory which we have seen was the theory of maximum density curve from Fuller's curve. So where the percentage passing can be determined from the aggregate sieve size and the maximum sieve size, and n is based upon the experimental results. The n value is 0.45. In addition to that, we also have seen about the maximum aggregate size and nominal maximum aggregate size. If we know the nominal maximum aggregate size, we can easily determine the maximum aggregate size. So what is nominal maximum aggregate size is, let us say we have multiple sieve sizes starting from 19, 19, 13.5, and 13.2, 9.5, 4.75, and so on. So out of all these sieve sizes, there must be one sieve size which is having more than 10% of the material retained on that sieve size. So let us say 13.2 is having 12% of the material retained on that sieve size. So the size just above to 13.2 is what we call it as NMAS. So corresponding to this, usually we also will see one problem that is being solved in the upcoming slides. So NMAS is, it is a sieve size. This is just one sieve size larger than the 10% retained sieve size, and maximum aggregate size is one sieve size larger than the NMAS. And in addition to that, we also have seen about the mineralogy of aggregates and its importance, and we have seen that mineralogy is not directly related to the performance of the asphalt mixture, but still it plays a vital role in the skid resistance of the asphalt mixture and also in the stripping of the asphalt mixture, because the bitumen is being coated on the aggregate surface. If the aggregate mineral properties or mineral composition is in such a way that it is not attracted to the bitumen, or it is more attracted to the water, then the aggregate surface can be stripped out of the bitumen. So that is the reason why the mineralogy of aggregates is kind of important for skid resistance and also for stripping. And we have seen that the siliceous aggregates and also calcareous aggregates, two types of aggregates, and we already know that bitumen is having the negative charge. So overall negative charge. When bitumen is having the overall negative charge, we have seen how they have been having a good bonding with calcareous aggregates. And we also will see few questions on these topics which we are discussing now in upcoming slides. And the polar groups, for example, the polar groups of acids of bitumen, when they are reacted with the active minerals of aggregates, they usually form the salts. So those salts are like sodium related salts, potassium related salts, and magnesium related salts. So when these salts come in contact with the water, they get dissolved. But we do not want that to happen. So we want that bond between the bitumen and the aggregate to be strong. So we do not want those salts to be dissolved. So we need to find the salts which are insoluble. So it was found that calcium salts are insoluble in water. That is the reason why lime means calcium oxide is usually used or mixed with the aggregates, so that it was acting as an anti-stripping agent. And when it comes to the pH of water also, base water has a poor bonding between the aggregate and bitumen. So in order to quantify that, we usually have two tests. One is the acid insoluble residue test and the polishing stone value test. This acid insoluble residue test is, let us say if we have set of aggregates, and when I subject these set of aggregates to the acids, let us say hydrochloric acid, HCl. So if the aggregate is of very weak in nature, then it gets dissolved. So when I say it gets dissolved, it converts into the liquid. There won't be any solids remain. So how do we do this test is, we take the aggregates and we add the HCl solution to the aggregates, and after particular cycles, we try to see how much material is solid material is remained. We try to see from the 75 micron sieve. If there is no material remained, means everything is soluble in the chlorine HCl. That means all of them are soluble. That is not recommended. So if the more solid material is remained, that means that is a more preferable aggregate type. That is how we do this acid insoluble test. And polishing stone value test is, we have the apparatus to determine this, so that the skid resistance of the aggregates can be determined in the laboratory. So from this theory, let us see few questions. After this, we can wind up the session. Which of the following aggregate is extrusive? So when I say extrusive, when the lava is coming from inside the earth crust to the top of the earth, there is a possibility that it can get solidified in between, like below it reaches to the top of the earth. Those type of solidification rocks are intrusive rocks. Sometimes that lava can come to the top of the earth and then it gets solidified. They are called as extrusive. So when it comes to the outside, it gets solidified very quickly. When it is inside, it will be solidified very slowly. So they are asking which of the following aggregate is the extrusive. So basalt is a type of extrusive rock. For improvement in the workability, which shape of the aggregate is desirable? So workability means when I am mixing these aggregates with the bitumen, there should not be a lot of resistance. It should be more comfortable to coat the bitumen onto the surface of aggregates and also in handling. So out of rounded, sub-rounded, angular and cubical, rounded aggregates, as far as the workability is concerned, rounded are better. But when it comes to the load transfer efficiency and all, which is more efficient, that you will be seeing in the upcoming lectures when we study about the shape characteristics of the aggregates. Which of the following crushers is typically used for giving shape to the aggregate particles? So if you could remember in the lectures, there were few type of crushers like jaw crusher, gyratory crusher, impact and cone crushers. So few of the crushers are to give the shape and few of the crushers are to eliminate the weak aggregates. So out of these options, they are asking which crushers are used for giving the shape to the aggregates. So both the impact crusher and cone crusher are especially to give the shape to the aggregates. So when I say shape, actually whether we wanted rounded aggregate shape or angular, when we do the SMA stone matrix asphalt, this is a type of gradation actually. So you actually require some type of aggregates. So based upon the required shape, we can change the crusher type and we can get the shape required. And if you see the fourth question, the sieve sizes and the corresponding weight retained is given below. Calculate the percentage passing each sieve. So this is a direct question. These are the sieve sizes starting from 19 mm to the dust. So weight retained on 19 mm, there is no weight retained. On 13.2 you can see 350 grams have been retained. The question is percentage passing each sieve, we have to calculate. Weight retained is already given, so you need to calculate the percentage passing. You can see here, so weight retained is already given till here. So if we add all these things, the total is 2200 grams. That means out of 2200 grams, 350 grams retained on 13.2, 400 grams retained on 9.5, so etc. So if I want to calculate the cumulative retain, so on 19, 0 is retained, 13.2, 350 enough. On 9.5, 400 is retained is what they have given. If I want to calculate on 9.5, already 400 is there. On 13.2, already 350 is retained. If some aggregates were retained on 13.2, they would definitely retain on 9.5. So you can calculate the cumulative in such a way. So these are the cumulative weights retained. Now this 350 is how much percentage in the total 2200. So 350 by 2200 into 100, you will get 16%. So 750 is nothing but 34% of 2200. So here I have calculated the percentage weight retained in cumulative. Why did I calculate the percentage weight retained cumulative is, in the question they have asked what is the percentage weight passing in cumulative. If I know the retained weight, so out of 100% is 0% is retained. That means 100 is passed. So if you deduct the 16 from the 100, 16 is retained, 100 minus 16 is passing. 34 is retained, 100 minus 34 is passing. So this 184.66, this is the cumulative weight passing on these particular sheets. This is what actually they have asked. Identify the nominal maximum aggregate size in this gradation as considered in the superfluid mix design. You can see the sieve sizes, 5 sieve sizes are given. Weight retained is given. They are asking out of all these 5 sieve sizes, which sieve size is the NMAS? We know that nominal maximum aggregate size is aggregate size above which minimum 10% of aggregate should be retained. So first if we know that sieve size, the sieve size higher, one sieve size higher to that would be NMAS. Let me explain the solution once. Let us say these are the sieve sizes given and these are the weights retained. So if I add all of that, total weight is 1300. So out of 1300 grams of aggregates, 30 grams are retained and 37.5, 70 grams retained and 26.5, etc. So if I want to calculate the percentage retained, so 30 grams is 30 divided by 1300 into 100 means 2%. So on 37.5, 2% is retained. But we want the sieve size which has minimum 10% retained. Let us come to the 26.5, 5% is retained. We don't want. Again 13.2, 38% is retained. So on 13.2, minimum more than 10% is retained. So one sieve size larger to that. That means 26.5 is our NMAS. I think you have understood now. Initially we have to find out which sieve size will have minimum 10% retained. Here 13.2. Once if we finalize that, we need to take the sieve size one size larger to that. That means just before that, that is 26.5. So 26.5 is the NMAS. Let us say if we want to know the maximum aggregate size, MAS. We know NMAS is 26.5. One size larger to that or before that, 37.5 will be maximum aggregate size. A gradation passing above the maximum density line is considered as. So maximum density line is the maximum density line usually passes to the origin when you draw a graph between sieve size and the percentage passing. So from the maximum density line, if your gradation is above that, that means it has more percentage passing. When we say more percentage passing means the fines are more. When the fines are more, that gradation would be fine gradation. Deviation of actual gradation from maximum density line in asphalt mixture is required for. So this we have actually discussed previously. For example, if we have a maximum density gradation, we cannot directly take that. We need to deviate from that. One of the main reasons which we have discussed is, if I take the maximum density gradation and that means entire aggregates are completely packed and there are no spaces. If there is no enough space, what happens? There will not be sufficient space available for the binder to expand, especially during the summer. So let us read the options once and let us see if anything is true. If we want to deviate from the maximum density line, they are saying, is there any reason? Increasing the voids between the mineral aggregates, okay. Thermal expansion of binder, okay. For improving the load bearing capacity, thermal expansion of binder and for improving the load bearing capacity, increasing the voids between aggregates and thermal expansion of binder, and of these. See, by now you could have understood. So we wanted to increase the air voids between the mineral aggregates and also we wanted to allow that thermal expansion of binder. And this is a practice question actually, exactly like the way we have solved previously. Using the table, calculate the percentage passing each C. If here it is 5% actually, 5% of stockpile A, 30% of B, 20% of C, and 45% of D are blended together. So you can see there are 4 stockpiles given, and if you observe this, only 19, 13.2, 9.5, 4.75, these aggregates are available in the stockpile A, and the remaining sizes are 0. If you can recall, the 4.75 and above are like coarse. So this stockpile actually have coarser gradation. And if you take the second stockpile, mostly it has few of coarse aggregates and few fine aggregates also. And if you take the stockpile C, it has only mid-range aggregates. And if we take the stockpile D, we have only fine gradation. So now we have to mix all of them in which ratio they have given. 5% of A means 0.05 into A plus 0.3 into B plus 0.2 into C plus 0.45 into D. So we have to multiply these factors. Then we have to calculate the percentage passing. So we already know the weights retained. We know how to calculate, so we can calculate the total weights. Then we can calculate the percentage weights retained. Then if you do the 100 minus, you will get the percentage passing also. Then we can multiply with these factors and we will get actually the percentage passing as this much. While evaluating the insoluble residue in carbonate aggregates, which solution is prepared? So as we discussed previously, when we perform the insoluble test, we have used the acid which is hydrochloric acid. So these are the questions. If you have any questions, you can ask. Otherwise, below our video also you can post. Okay then. Thank you.